Behind every groundbreaking AI model and every climate simulation lies a hidden, boiling reality. The world's fastest supercomputers are essentially massive heaters that happen to do math. As we push toward the next frontier of zeta-scale computing, we are facing a statistical wall, not of logic, but of thermodynamics. Today, we go beyond the benchmarks to analyze the staggering energy costs of the digital age and the radical cooling technologies attempting to save it. Welcome back to Algonexa. In our last analysis, we compared quantum speeds to traditional HPC, but today we tackle the power problem. We are diving into a statistical deep dive of power usage effectiveness, the carbon footprint of the world's top 500 supercomputers, and the engineering marvels that keep these silicon giants from melting. By the end of this video, you'll understand why the future of AI is no longer just about faster chips, it's about smarter cooling. Let's start with the raw numbers. The Frontier supercomputer, currently the world's fastest, consumes roughly 22.7 megawatts of power. To put that in perspective, that is enough to power over 16,000 homes simultaneously. As we look at the historical data from the top 500 list, energy consumption has grown exponentially. In 2010, the top system used roughly 7 megawatts. Today, we are projecting zeta-scale systems that could require over 500 megawatts, essentially requiring their own dedicated nuclear power plants. The statistics show that we are reaching a point where the cost of electricity is beginning to outpace the cost of the hardware itself.
How do we measure if a data center is actually efficient? The industry standard is PUE, or Power Usage Effectiveness. A PUE of 1.0 would mean every watt of power goes directly into computing. Anything above that is overhead, mostly cooling. While the average data center sits around 1.5, the world's most advanced HPC sites are pushing down toward 1.03. We analyze the data from the Green 500 list, which ranks supercomputers by gigaflops per watt. The trend is clear. The most efficient systems aren't just using faster processors. They are utilizing advanced warm water cooling loops that eliminate the need for energy-hungry mechanical chillers. Traditional air cooling is dying. Air is a poor conductor of heat, and as chip TDP, thermal design power, exceeds 700 watts per GPU, fans simply cannot move enough air to keep up. The data shows a massive shift toward liquid-to-chip cooling and, more radically, two-phase immersion cooling. In immersion systems, the entire server is dunked into a non-conductive fluorocarbon liquid. When the chips get hot, the liquid boils, carrying heat away through latent heat of vaporization. Our statistical comparison shows that immersion cooling can reduce cooling energy consumption by up to 90% compared to traditional CROC units. If we can't stop the heat, can we use it? Data centers are essentially the world's most expensive boilers. New statistical models are looking at district heating integration. In cities like Stockholm and Helsinki, the waste heat from HPC clusters is being pumped directly into the municipal heating grids to warm thousands of apartments. We've analyzed the ROI of heat recovery systems, and for large-scale enterprise clusters, the ability to sell waste heat back to the grid is becoming a vital part of the economic benchmark for new facilities. Finally, we must look at the statistical irony of quantum computing. While a quantum processor uses almost no power to calculate, it requires a dilution refrigerator to reach temperatures near 10 millikelvin, colder than outer space. While the power per calculation for quantum is theoretically superior, the baseload power required to maintain that cryogenic state is constant. As we scale from hundreds to millions of qubits, the engineering challenge shifts from how do we cool the chip to how do we scale the refrigerator. The data proves that the next decade of computing won't just be won by the company with the best code, but by the one with the best plumbing. What do you think is the most viable path forward? Massive immersion tanks or moving our data centers to the Arctic? Let me know in the comments below. If you want more data-driven deep dives into the infrastructure of the future, make sure to like this video and subscribe to Algonexa. We're building a community of tech professionals who look beyond the hype and into the hard numbers. The future is fast, but only if we can keep it cool. Thanks for watching Algonexa, and we'll see you in the next deep dive.